Last video on this computing math section. And in this section, we're going to do something a little bit different than what we were working with before with binary and hexadecimal. But I wanted to introduce this because it is an operation that comes up quite a bit. In fact, we've already seen it in the math that we've been doing, talking about converting between binary, hexadecimal, and decimal. And that is the idea of modular arithmetic. So we saw how when we were looking to do those conversions, we were really interested in the remainder when we were doing division, and having that remainder then told us what we needed to do next, basically, and it has some sort of meaning to it. And it turns out that this is actually something that can happen a lot in the course of doing programming or understanding how programming works. So it's useful enough to describe it using its own operation. Now, before we get into this, let's just remember division, right? And remember an integer, which we talked about in the previous section, is a number from the following set. When we mathematicians think about this, we think about starting with 0, you can count up by 1, and you can basically count as far as you like. So we'll just denote some ellipses there to denote that in mathematics this can continue on forever and ever and ever. But then the same also goes in the negative direction. So you can basically think about the integers as being all of the numbers that you could count to from 0 by either counting up or counting down. So in other words, it is all of the positive or negative whole numbers along with 0. And one of the operations we learned how to do back in grade school is how to divide one integer by another. And remember, what ends up happening is we end up getting some equation that looks like the following. When we divide a by b, we get some quotient q and some remainder r. So the name that we're going to take for this operation when we're really focused on the remainder, not necessarily the quotient, is called the modulo operator, often abbreviated as mod. That's what we'll do in this course. And a way to represent this, if we're not interested in how much it divides by, right? We're interested in what's left over after we attempt to do that division. So the way that we can denote this same thing here is that a mod b is equal to r. Let's do an example here. Find the remainder when dividing 16 by 5 and write the answer using the mod notation. And I do a little bit of overkill. Let's just remember long division here for a second, right? If I put 16 there and I want to know how many times is 5 going to 16, well, the greatest number that I can fit in there is 3 times 5. And remember, we take 3 times 5, we get 15. We subtract it, we're left with 1. At this point, 5 can't go into 1 at all, so that is our remainder. Now, the way that we write this using the mod notation is that when I take 16 and I'm interested in its remainder when I divide by 5, the thing I get is 1. For the purposes of doing this modulo operation, we're actually kind of not really concerned with what the quotient is at all. We're really just focused on the remainder. And the modulo operation happens a lot when we're doing some sort of loops in computing. Basically, anytime that there's a pattern that repeats, let's look at an example here. Let's find the remainder of the following things when we're dividing by 3. So we'll do that for 0, 1, 2, 3, 4, 5, and 6, and write our answer using the mod notation. So when I do 0 divided by 3, I get, well, nothing, right? And let me write remainder, I'll just abbreviate that with r to save some space. We get nothing left over, right? Try to split $0 among 3 people, no one gets anything, and there's nothing left over, right? So here, the way we would say this is that 0 mod 3, right? It's always the second number is the thing we're dividing by. Well, the remainder that we get when we divide 0 by 3 is 0. What about 1 divided by 3? Well, again, I can't divide 1 into 3 evenly, and I will have 1 left over. So 1 mod 3 is 1, right? Because that's the remainder. Again, 2 divided by 3, we still can't divide it evenly at all. We get 0 with a remainder of 2 left over, which is to say that 2 mod 3 is equal to 2. Now, if we come back to 3, right, I'm just adding 1 to the thing that I'm dividing by 3. Well, now 3 does go evenly into 3 with none left over. So 3 mod 3 is also 0, right? Because there is no remainder. When we do 4 mod 3, again, we'll get it to go in once with 1 left over. So 4 mod 3 is equal to 1. And then lastly, 5 divided by 3, well, we can have 3 go into 5 once with a remainder of 2, which is to say that 5 mod 3 is equal to 2. And you may have already picked up on the pattern, in which case this might have been boring for a second there. You'll note here, every time I add 1, my remainder goes up by 1. But once I get to here, when I add 1 to that one, we cycle back to 0. So it goes this pattern of 0, 1, 2, 0, 1, 2. And following along in this pattern, 6 mod 3 is going to take us back to 0. Because again, when we divide 6 by 3, we'll get 2. With none left over, that remainder here is our answer to this modulo operator. Now, one way that this can get described, and you'll see some exercise like this in the homework, is to imagine the modulo operation as basically being like a clock, right? When we think about a standard analog clock, or for that matter, a digital clock, there's only a certain set of numbers that we can describe using that clock. And eventually, once we get through all those numbers, we cycle back and start counting again. So for instance, analog clocks are typically 12-hour clocks. We have AM and PM. If we count 51 hours starting at the top of the clock, and we're counting on a 12-hour clock, what number do we end up pointing at? Well, every 12-hour cycle, we will come back up to the top. So we are at the top, at the top after 12 hours, and then after another 12 hours, so after 24 hours, after another 12 hours at 36, and after another 12 hours at 48. Well, if we counted another 12 hours from there, we get to 60, which is past 51, so clearly not what I want. But we can just ask how much further is 51 than 48? Well, the answer would be 3. So we would stop at 3. And really, when we think about this, what we have just done is we have just done the modulo operation, right? We wanted to figure out, if I divide 51 by 12, I'm going to get some number of even complete cycles and then have something left over. So when I take 51 and I try to figure out what its remainder is when I divide by 12, the thing I'm left with is 3. So this is basically, sometimes modular arithmetic is called clock arithmetic, because we're really thinking about all of the numbers as being on a clock. And we'll kind of build on this in a little bit, but basically we can think about this like a normal clock with one slight modification. So instead of counting at 12 like we'll think about it more like a military sort of scale, where we're going to count starting at 0. And we're going to count upward from there. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then back to 0. And those are all of the numbers that we're going to be dealing with, right? We're only thinking about the integers here, so we're not thinking about like 1.5 or anything like that, just the integers that we're working with. So now if we want to find any sort of operation A mod B, we can think about the following steps. Since we're dividing by whatever number is here, we can construct a clock that has B number of steps there, starting counting at 0, ending counting at 1 less than B. And then starting at 0, we can move the clock A steps around, and whatever number we stop at is the solution. So let's find 13 mod 4 with this operation, this procedure. In other words, think about what number we're going to arrive at if we count to 13 on a 4-hour clock. Now, you might actually already have the idea in your head with this, but let's just build this clock and see how this operation works. If I'm counting to 13, starting up here, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. So I'm going to stop counting at 1. So that means that 13 mod 4 is equal to 1. Note that this is the same as we were thinking about before. It's just instead of describing this in terms of like the division algorithm like we were doing a moment ago, we are noting that every time we complete one of these cycles of 4, we get up back to the top. So this is really just kind of asking, where do I end up within this cycle? So again, this is why this stuff is really applicable for things like loops, is because loops in computing often operate on this sort of a cycle, and knowing this modular operation can tell you what part of the cycle you end up in after a certain number of steps or a certain amount of time. Let's do a couple more exercises like this. 27 mod 5. So for this one, we're going to build a clock that has 5 numbers on it. And remember, we start counting at 0, so we're going to end counting at 4. And now we're going to count along this clock 27 steps. So starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So that's going to equal 2. And again, note something that happened while we were doing here. Anytime we ended on a multiple of 5, we ended back up here. So here we can note multiples of 5 all end up at the top. So you can basically think about this as, okay, what's the biggest multiple of 5 that's less than this number? In that case, that's going to be 25. And then how many numbers beyond that is 25? In fact, that is exactly what we're doing when we're thinking about the remainder doing division. So if we find 32 mod 5, well, since we already noted multiples of 5 will take us up to this clock, 30 steps would take us up to here. 1, 2 more, 32 mod 5 would equal 2. So both of these numbers have the same remainder when dividing by 5. So again, thinking back to that like computing idea that doing an operation within a loop a certain number of times might take us to a certain step. If we have a sort of cycle of 5, doing 27 steps or 32 steps within that cycle is going to get us ending on the same spot. In that sort of circumstance, we could note that there's a similarity between 27 and 32. If we knew that we were in that step within the program, it could have been that we had 27 steps that happened, could be that we had 32 steps that happened. But the similarity is noteworthy enough to give its own definition here. Again, we're just sort of scraping the surface with the idea. There is so much more that we can say about congruence, but we're just going to introduce some basic ideas that are relevant for understanding how the operation gets used in computing. So we say that two numbers a and b are congruent mod n if they have the same remainder when dividing by n. So if those two things are the same, again, we could say that a mod n is equal to b mod n. So whatever remainder we get, so like we note from that last example we just did, 27 mod 5 is actually equal to 32 mod 5. And if we had that sort of cycle of steps, they would both end up at that same step. So they have that similarity to them. So they're, in a certain sense, kind of very similar. The way that we are going to denote this with a new little mathematical operation here is we're going to use this symbol. It's an equal sign with another bar underneath it. We kind of use this symbol to denote it's sort of like they're equal. They're equal within this system, thinking about it in this clock step, right? If you are completely disoriented and you look at a clock, and you have no idea what time it is, but if the clock reads 5, it could either be 5 a.m. or it could be 5 p.m., right? Which you can think about as like 17 on a military clock. So in a 12-hour analog clock, looking at the clock, we can't tell the difference between 5 and 17. So we could also note, for instance, that 5 would be the same thing as 17 mod 12. So those two numbers would be congruent to one another. Let's just do a quick little bit of practice here, determine whether the following statements are true or false. So is 16 congruent to 4 mod 12? Remember what this is asking is, do they have the same remainder when we're dividing by 12? Well, if I find 16 mod 12, 12 can go into 16 once with 4 left over. So that remainder is 4. And of course, if we take 4 mod 12, well, 12 doesn't go into 4 at all. So we would get 4 as a result, so this is true. 16 and 4 both have the same remainder when dividing by 12. What about 19 and 33 mod 3? Well, let's compute both of these things. Note we're trying to find the remainder when dividing each of these numbers by 3. So 19 mod 3, so we could divide 19 by 3 6 times, we get 18 with 1 left over. If I did 33 mod 3, well, 33 is actually a multiple of 3, right? It's 3 times 11. You can see how knowing your multiplication tables is pretty darn useful for these sorts of things. We'll talk about how to use a calculator as well. We've seen that already with conversion in a previous section. But 33 mod 3, since it is a multiple of 3, anytime we have a multiple, that modular value is going to be 0. Because if you're a multiple of 3, it means that when you divide that number by 3, you get a remainder of 0, divides evenly. So these two things are different values. So this would be false, right? They are not congruent mod 3. Let's do this last one a little bit trickier, and that'll require us to come back to our calculator here. 19 and 14, we want to know, are they congruent mod 11? Now 11 is a trickier number to get a handle on, so we might want to think about how to use our calculator to find this. A lot of computing languages have a modular operation embedded in them. Once upon a time I learned Java, and I think it was the percent symbol, if I recall correctly. But again, programming languages vary, so just check with whatever manual you're working with to figure out what that operation is going to be. So you might be able to find a computing software or something that will do that for you, but a lot of handheld calculators, for whatever reason, don't necessarily have this programmed, or if they do, you have to do a little bit of work to find it. Feel free to Google your calculator if you want to look up how. But barring that, there's a surefire way to do this. We talked about this before, right? If I want to find the remainder when I divide 19 by 11, I can just ask myself, well, what's going to happen? Sorry, did I say 19? I'm at 91. What's going to happen if I divide 91 by 11? So my calculator gives me this decimal when I do this, and there's a couple of ways to go about figuring this out, right? I can see that it divides in evenly 8 times with some fraction left over. So we talked about how what we could do is just subtract away that 8. This is the fraction that's corresponding to my remainder. Now I'm going to show you the all-purpose way to do this that will work regardless of what number that you're working with. Since this fraction represents the fraction that's being divided by 11 that couldn't divide in cleanly, I'm going to take that and multiply it by 11 to get that. So again, when I divide 91 by 11, the thing that I get, let me just do that one more time to show you, I get 8 with a remainder of 3. So again, how did I know 3? When I subtracted that thing and then multiplied it by 11, voila, that's my remainder. The other way, and this doesn't work all the time because sometimes your calculator might simplify a fraction further than it is useful to do for this operation, but with this one we're actually safe to do it. If I divide 91 by 11 and then use my fraction to decimal conversion button, this one's going to present this as a mixed number 8 and 3/11. So again, we see my remainder here is 3. So 91 mod 11 is equal to 3. That's the remainder when I divide 91 by 11. And 14 mod 11, we can do this one without a calculator, right? If I divide 14 by 11, 11 is going to go in once. If I subtract away 11, I have 3 left over. So yes, they both have a remainder of 3 when I divide by 11. So this is a true statement. All right, so we've already hinted at this idea of where congruence shows up because there's a lot of circumstances where two congruent numbers are functionally the same. They're sort of identical, which is why we use this sort of notation. They're not exactly equal, but within a given context, they serve the same purpose. So now let's put this back in the clock context. If it's currently 7 o'clock on a 12-hour clock, and there's some computer process that's running for 19 hours, we can ask, what is the clock going to read when the process is complete? Now, there's a few ways to think about this, but if we're on a 12-hour clock, we could ask ourselves, starting counting at 7, how long is it going to take before it resets? So if I'm starting at 7, I have to count 19 hours. I could figure out how long is it going to take to reset and then keep counting from there. Or another thing I could do would be add 19 to this. And again, thinking about this on a clock, right? So when I start at 7 and then add 19 to this, I would get 26 steps along the clock. In other words, to start counting at 7 means I can imagine starting at 0 and then adding 7 to that, and then going 19 more steps. Well, we've seen that clock before. We can come back to that clock we saw on the previous page, this one right here. Right? If I started here, counted 7 steps, count another 12 steps, right, it would get me to here, and then 19 is 7 more than that. So if I go another 7 steps, I'll get 1, 2, 3, 4, 5, 6, 7, and I will end at 2, which we can note 26 steps along the clock will end us at 2. And very frequently in computing, we're doing this sort of operation where we have some number of steps take place, we allow another certain number of steps to take place, and we want to know where is it that we're going to end up, and that is the basic idea of modular arithmetic. So when I'm doing a plus b mod n, what that is asking me to find is what is the remainder I get when I divide a plus b by n. So we can note it's really no different than the notation we've used before. When I say that 91 mod 11 is 3, this here would be saying that previous step above there would be 7 plus 19. When I'm thinking about this mod 12 on a 12-hour clock, that equals 2, because that is the remainder I get when I add 7 plus 19, or 26, by 12. And then the exact same operation for subtraction. A minus b gets us the remainder, a minus b mod n is the remainder we get when we divide a minus b by n. Let's look at 2 examples of that, and then we have 1 application, and then we'll wrap up this section. So let's do the result here using modular arithmetic, 13 plus 32 mod 9. Well, there's multiple ways of doing this, but the easiest way is to just ask ourselves, okay, what do I get when I add 13 and 32? It's going to be 45. And then what is the remainder that I get when I divide 45 by 9? Well, 45 is actually a multiple of 9, so that divides evenly, so we will get a remainder of 0 when I divide 45 by 9. Exact same idea for doing subtractions. These are actually pretty straightforward, simple kind of problems here. If I want to find 105 minus 38 mod 7, well, again, feel free if you need to use a calculator for some of that subtraction part, that's okay, right? 105 minus 38 gets us 67, and now we want to find that mod 7. Well, the way that I would do this is I would think, I know that 70 is a multiple of 7, so I can count backwards from there, right? I know that 70 would be congruent to 0 mod 7. So then if I just counted down from there, if I count down from 70, the next number below that, 69, would be congruent to 1 less than this. But remember, we're only allowing ourselves the numbers 0 through 6. So if we went down by 1, we would go back to 6. If I went down again to 68, that would be congruent to 5. If I went down to 67, that would be congruent to 4. Again, just to show you the other ways of doing this, if I take 65 and divide it by 7, I'm going to get 9 with some things left over. I could convert that from a fraction to a decimal. That tells me I've got 9 and 4/7. That number that's being divided by 7 is our modular answer here. So believe it or not, again, this modular arithmetic actually has a lot of applications to algorithms and cybersecurity. And among other things, one of the examples that you'll encounter in the homework is the notion of what's called a check